All right, hi. So I'm Nick. I don't think I'm quite as amazing as he just suggested, but I'll do my best. So what we're going to talk about today is just, well, it's machine learning with H2O.ai. So H2O is the company, and what we've been doing on Google Cloud. This is leading up to our talk tomorrow, which is actually going to be at Google Next. We're going to be discussing scalable machine learning on Kubeflow, which is a open source platform that Google has developed on top of the Kubernetes engine. And then there will also be another talk with Erin Liddell, and she's going to be talking about bias in machine learning, and that's also at Google Next. So if you guys happen to be attending or have a chance to show up, then feel free to swing by, and you can even pick up one of these nice little post-it cards, I guess, that have information on it. So yeah, with that, let's jump right in. As you can see on the title, if you can't see the title, by the way, it just says machine learning with H2O. It's nothing exciting. So moving on. So what is H2O? H2O is a company we founded in 2012. At the moment, we have about $75 million in funding, and from several very large investors, NVIDIA, Wells Fargo, to name a few. We have a couple different products which we'll go over, but there's the two major ones, which are the open source as well as the enterprise product, which we'll also talk about. We are a leader in the Gartner Magic Quadrant. They rated us in the top right corner, which I believe has been told is the most important one. And we have a team of about 90 AI experts. Actually, no, this might be a little outdated. It's about 110 at this moment, of which we have 5 of the world's top 100 Kaggle grandmasters. So lots of really smart people doing a lot of really smart things. Yeah, so offices in London, Mountain View, Prague, and India. So this is just another quick look at the Magic Quadrant. So as you can see, we're up in the completeness of vision, and as well as having the ability to execute. So just overall, very strong performer in the quadrant. There are so many people that I think it's upwards of 400,000 companies / data scientists are using us. And customers gave us the highest overall score as far as customer support goes. So we are super responsive to our customers and our community. So I'm really actually glad to see so many people here. We weren't really expecting maybe half as many as you guys. So this is awesome. I'm glad you all showed up. Quick overview of our product suite. I'm just going to try and keep this short so that we can get a demo in, as well as have some Q&A and maybe a little bit of like Socratic discussion stuff. So just so you guys know, I'm going to breeze through. If you have questions, raise your hands. So yeah, so our open source platform, as you can see on the left, is comprised of H2O, sparkling water, and H2O for GPU. H2O is the base kind of platform, and sparkling water and H2O for GPU kind of add on to that base platform. So H2O is a distributed in-memory application which allows you to create clusters of machines which can do data science, and we hand roll a lot of our of the other algorithms. It's very similar to scikit-learn, but we utilize the knowledge that our data scientists bring to the table to make the algorithms that much faster, that much more effective. Sparkling water is H2O3, but on Spark, so that you can deploy it on your Spark cluster and do all the great things that you can in Spark, including data munging and some of the more exploratory data science aspects before actually putting it through the H2O algorithms and getting the inference out. H2O for GPU, as you can tell, is just H2O, but optimized for GPUs. Nothing super complicated about that one. And finally, Driverless AI. Driverless AI is our enterprise software. I think it was launched close to maybe a year and a half ago at this point. And basically what it comes down to is it's the idea of just the full machine learning pipeline. Basically, the idea is you give it data and it will do some feature engineering for you. It will create a model as well as create a model for you and allow you to perform inference on said model. And that one is enterprise, so you'd have to buy a license or utilize one of the cloud offerings that offer pay-as-you-go pricing. So quick overview of H2O3. Again, it's basically a more optimized version of scikit-learn. It uses Java on the back end, so it's very fast and it's highly optimized, as well as being fairly lightweight, so you don't have to run it on a ton of storage or anything like that. And it's really good with big data. So the idea being is that you can distribute the data across multiple nodes on your cluster, and it will perform fairly admirably. As you can see here, there are basically a couple different algorithms that you can use. You'll see a lot of familiar ones, random forest, GBMs. For NLP, you've got word2vec, or you have dimension reduction or clustering for more non-targeted data sets. So this is kind of the idea of the simplified machine learning pipeline. First, you get your data. You do some sort of transformation so that you get a static data set, and then build the model off of that, train the model off of that. Ultimately, you get moving from left to right. So high-level architecture, essentially you can have your data stored in HDFS on local disk, SQL, NFS, or in this case GCS, and this is directed to the idea that we are in a meetup for Google stuff. And then once you have it in there, you can just pull that in from your data store into H2O using either Python, R, or H2O Flow. H2O Flow is essentially like a notebook-style GUI that allows for users who are not super coding experienced to allow them to do some of the same things that someone who could also do it in Python would be able to do. And from here, you can perform exploratory analysis, do some feature engineering, get your model, train your model, and as well as do scoring and inference on said model. OK, and driverless AI. So driverless AI, basically the idea is that it is an expert data scientist in a box. It's the whole goal of H2O AI's driverless AI is to kind of make machine learning more accessible to everybody, to BI people, business intelligence people, to make it available to analysts who don't necessarily have the coding experience, the 10 years Python background that a lot of data scientists are expected to have. What it does is it provides a GUI, but also a Python client as well as a Java client that enables you to do the same things in driverless, but also you can use the GUI so that it's more point and click for people who don't have that coding experience. So now the difference being is if you saw the original one, there's a nice blue box over here. And that's the only difference, guys, is just a blue box. But ultimately, what it comes down to is that we will do, or driverless AI rather, will do the feature engineering for you. It takes several different, and mind you, this is not like the same idea as feature engineering of like some data scientists will go in and say, oh, I've known that this column will always do, or always give me boost. That in the sense of domain knowledge is not what driverless AI does. Driverless AI is taking all the statistical inference and all the statistical calculations, like converting categorical values to numerics, or using binning to decide whether or not those categorical values are valuable in reference to the other ones. So that kind of feature engineering is super helpful because a lot of people don't want to have to spend time doing all that other work and then deciding if those features are actually valuable. So that's what driverless AI does. And then you can add on top of that the domain knowledge of, oh, if I take this value and take the log of it and then also like transform it upside down, and domain knowledge kind of things where you know exactly what you're doing and you've been doing it for the past 10 years. You can add that in along as an extra column, and driverless AI will accept it and give you that additional boost on top of the boost that you get from the automated feature engineering that comes out of driverless AI. And then ultimately, they'll build you a model, and it's exported as a Mojo or Pojo. Mojo meaning memory optimized Java object, or Pojo meaning plain old Java object. Or you can use a Python scoring pipeline. And all of them will be, basically you can deploy them on a standard VM or in your Kubernetes cluster or where have you, and it will allow you to do scoring and inference. So why driverless AI? Driverless AI is good for several different reasons. One, it does the feature engineering, which is one of my favorite things. Two, it's super fast. It's optimized for GPUs, which makes it a lot faster. And since the fact that there's a lot of time that goes into building these feature engineering pipelines, because we do it automatically, it means that one, you don't have to spend weeks or months doing these feature engineering pipelines. They come to you automatically. And finally, is the fact that it's interpretable. The major thing that comes with one of the major things that comes with driverless AI is the fact that you get MLI, which is machine learning interpretability. It's a package that we bake into driverless AI. Basically what it does is it builds surrogate models of any model that you train in driverless AI, and it interprets what the model's doing in order to give out to you a reason why driverless AI decided to make this specific model the way it did. So it gives you reason codes, it gives you kind of a decision tree telling you why it took a specific path, so on and so forth. One more reason, accuracy. As you can see I guess as you can see in this corner over here, you can see that it's it does fairly well. Usually top about 5% in most Kaggle competitions. Compared to a lot of these people, like driverless AI took maybe a couple hours to train, whereas a lot of these people spend a week, month on a Kaggle competition just to even rank, let alone come in the top 5%. They won't let us win anything, by the way. Otherwise, that'd be a lot of our revenue right there. Okay, so just a quick example of our auto feature generation. So as you can see, it handles text automatically, does some singular value decomposition to get those components, and that's what they actually put into each columns, or each row for that column would be like the component for that specific row. We also do clustering. And you can see that in this section right here, so in the black box, which is of course really hard to see because it's all blurry here, is you can see like there's some of the more, the ones that we made, so like numeric to categorical target encoding, which is this one, or there's like the original cost, which is this one right here. And so this is basically driverless AI saying, did we or did we not think that this was valuable, and why? So at the top you see the first one is a value of 1, and that means that basically that's the most important feature at this moment in this specific iteration. And as you continue down, it'll give you lower and lower values. And as you continue, basically you can see that there's some that are we generated, some are just features that are in the data set that were just important because they were important. So moving forward, we'll do, this is kind of like just showing a couple of the pipelines that we've suggested. This is more on the GCP side. But basically, H2O plus Kubeflow. Now, Kubeflow is basically baseline Kubernetes, but on top of that, they built a layer of abstraction that allows you to deploy Kubernetes pods and deployments in much more efficiently. Basically, instead of having multiple YAML files or manifest files, you can have a single template that you then pass keywords to, and the keyword arguments will actually define the deployment as it is. You can find our repo right now is H2O-Kubeflow on GitHub. It's public. I would encourage you guys to try it out. It's really cool. And basically what it does is it allows you to kind of atomize. I don't know if, is everyone familiar here with Kubernetes, or am I kind of waving my hands like this a little bit? I see one person, 2 people. Okay, so quick run through of Kubernetes. Kubernetes is basically if you have 7 machines and they each have 4 cores and 16 gigabytes RAM, so like 7 of these guys right here up in front that I'm using. You can mush them all together. Yes, technical term, mush. And, and basically what you get is you get a machine that is 4 times 7, so 28, plus 16 times 7, which is a bigger number. I did not study math in college. But anyway, so once you get there, then Kubernetes allows you to kind of atomize this. So what that means is if one of the deployments that I needed only wanted, say, 1 core and 4 gigs RAM, I can easily create one. That becomes one Kubernetes pod. And then the rest of the machine is still available for all the other things that I want to do with it. So I could theoretically spin up 3 more additional pods that do the exact same thing, or I can spin up one really big pod that consumes the rest of the resources, or I could spin up a cluster of 3 pods that consumes the resources on the remaining resources on that machine, plus 2 more machines. So that's Kubernetes in a nutshell. Kubeflow is basically an extra layer on top that allows you to template what I just explained. So this is a couple of our deployment options. Basically, you can ingest some data. It's the same idea. Ultimately, you get a model from our product, either H2O or Driverless AI, and you then deploy it on another machine, either using the Mojo or Pojo. And from there, you can expose it as an open API. You can expose it as just like like a REST server, and that will allow you to send requests to it and get in-time scoring or real-time scoring, or you could do like batch scoring as well. So you pass it a batch of rows, and it'll score those and send it back to somewhere you can store it in a SQL database somewhere else. And then this is kind of like if we wanted to use GCP entirely. Kind of a high-level deployment. So this utilizes Spark. Basically, if you have your data stored in BigQuery or cloud storage, Google Dataproc is Google's version of Spark. It's basically Apache Spark, but it's a turnkey solution. So you just type in, Google launch Dataproc, and then it'll turn it on for you, which is really nice because you don't have to set it up. And then we can run on top of that. So we place sparkling water on top. You can do your data munging. You can do some preliminary like EDA and things like that. And then ultimately you can output some file to Driverless AI, where Driverless AI is running on GCE or Google Compute Engine. Get your final model, which has taken all the kind of calculations that you've done in Spark, and now will do its own. And then finally, you can output it as a Mojo for serving inference. Another one is if you wanted to skip Spark, or you had your data directly in BigQuery, you could do just straight SQL queries from BigQuery into Driverless AI. We have a built-in integration point with all the Google storage platforms, so that we can actually just ingest data straight from Google and run Driverless AI on those. And then again, inference through the Mojo, the Pojo, or the scoring pipeline. So I think that's about it. I think I went really quick through this because I wanted to talk a little bit more about some cool things in Driverless AI and H2O. So what I've done here is basically this is, as you can tell right here, the Google Cloud Platform. It's pretty cool. I've made a couple deployments myself. So this one is a cluster of H2O3. And then on the other tab, we have a cluster, a virtual machine running Driverless AI. So these are very much turnkey solutions, which is really great. If you go to GCP, like console.google.com, and go to the marketplace. I'm just going to show you this really quick because if anyone does have a Google Cloud account, I think if not, then you can actually launch or get one, and it gives you like $300 credit. So it's actually pretty good. You can play with this stuff pretty easily. And if you search H2O.ai, you can see all our 3 offerings right now. So there's the licensed version of Driverless AI. There's also a pay-as-you-go offering, which basically will charge you per hour usage. And then there's also the cluster of H2O3. So I launched a pay-as-you-go option and also a cluster version, or rather an H2O3 cluster. And so we can go take a look at the H2O3 cluster first. Basically what I have to do is just click connect, which is really awesome, and it'll sign you in. They do expose a password and a username for you, but I had already signed in, so it just kind of dropped me into this And this is what I was talking about, H2O flow. So H2O flow is basically the same idea. It gives me the ability to use all of the same things that are in H2O, but in a GUI, which is really nice if you don't have, you know, the coding skills necessary, or you know, are still kind of getting into it. So you maybe know or are comfortable with Python, but not necessarily ready for that yet. Now, the other thing that you could do is if you do Jupyter Notebook, you can actually just connect through the H2O client. And so this is about as much coding as we're going to do, by the way. I'm not going to do like a ton of coding. I'm just kind of showing you like what you would do. So as long as you have H2O installed on your machine as well, you can actually utilize the H2O client. So h2o.connect. And then the actual instructions are right here. So I would do this. Is there, Mark, was there or Mike, was there a request?
I'm just going to turn them away.
Gotcha. Okay. H2O connect, and then auth equals username and password. So we do protect this with SSL encryption. This is a cloud offering, so it is on, you know, Google Cloud. So obviously it's always nice when we have some you know, extra protection. And H2AI. Don't worry, if you guys copy these passwords, I do turn off the machine and, you know, afterwards, so you can use it for exactly half an hour. I apologize. I have and this is why I didn't want to do any coding. I have an older version of H2O on this machine right here, which is the reason why I'm getting connection errors. So yeah, make sure that your machine has the most up-to-date version of H2O. Otherwise, that's what you end up with. But this is basically what you end up with, and you can use the Python client, which can be visible at docs.h2o.ai app. So H2O user guide, and you can actually take a look. There's some really good demos. So if you have an opportunity to launch a cluster, feel free to, and just play around with the Python client. It's really fun. And there's a lot of good algorithms. I apologize that it's just that I haven't updated my my H2O software on my machine, so that's a little awkward. Okay, well, let's move on. So we're going to go to Driverless AI. Now, Driverless AI, this is actually kind of small already, so I'm going to make this a bit bigger here. Hold on a second. There we go. So Driverless AI is the enterprise version of our company. Basically, it takes a lot of the things that we did in H2O and optimizes them for GPUs, also makes them more efficient, as well as adds on some other cool things like the MLI platform, as well as the auto feature generation. So from here, we actually have the opportunity of importing from a couple different file systems. So AWS, Hadoop, if you have a Hadoop cluster running with your data, straight from the file, or straight from your file system on your VM, or on your regular machine. So this is on-prem and closed off to the internet and just like behind 7 different firewalls, like I know that a couple different banks use. You can just have the data on disk. Obviously, that makes the most sense, right? All the other ones are kind of extra. But from here, you can go to cloud storage, and it would be GS, H2O, GCS, pub. So this is our open, basically it's our public data. So it's got a couple demo data sets that we can play with. The one I'm going to use is a fairly straightforward data set. It's a credit card data set from a Chinese company. And basically all it's doing is predicting whether or not you can default on the next month's payment. So from here, there's the first step that you can do is you actually have a couple options just from the data set side. So just in case I breeze through this really quickly, is basically I went to Google Cloud Storage and I selected from the specific endpoint that I chose. So I typed it in. I selected the data set that I wanted and simply clicked import. What that does is on the back end, it's going to create something called a Pi data table. Pi data table is our basically version of our data table. So I don't know if anyone's familiar with that, but it's one of the fastest in-memory data tables, or like data frames that you can have. And what it allows us to do is all the really cool stuff. So like our feature engineering, our feature munging, all the extra model training, things like that. It's just super fast and it allows us to be even faster therefore. Next, we can do a couple things. So you can describe the data set. This is a lot similar to, if anyone's familiar with pandas, pd.describe. That's kind of, or .info. This is what you're getting, is you get some statistical measures of what's going on. You also get, is it a bool? Is it a, what type is it? Is it an integer? Things like that. After that, we have another package. This is also straight from Driverless AI, which is called AutoViz. AutoViz basically gives you, like, I don't know if anyone has had this kind of happen, but basically the idea behind it is you're trying to describe visually what you're trying to see on the data set. And a lot of data scientists, they have to create the histogram themselves and say, okay, well, what are my settings? So what H2O does provide through Driverless AI is a lot of the visualizations that you yourself as a data scientist would usually make. So for example, an outlier plot. So if you take a look, this one is specifically 4-column pay amount 4. So that's the 4th payment amount in the data set. And you can actually click on, you can see here, I'm kind of hoping you can see here, there's one dot, and basically this is an outlier as compared to the rest of the data, or for that specific column. So that column is saying, well, most of our data is binned around 0 and a little bit, basically anything below $50,000 is most of the payments. And so now we've got this one payment which is enormous, and it's like, well, looks like $500,000. So someone either went in and paid $500,000 just like that. I don't know how many people have $500,000 laying around, but I don't. Or this could just be an accident. This could be a typo. Someone probably paid $50,000 and somehow an extra 0 got appended to it, right? So these are useful for either finding out why a specific data set is potentially acting weird, or noticing if there's errors in your data. Things like that prior to launching an experiment, right? Afterwards, now that you've kind of inspected the data and you've kind of played around with it, looked at it, you can say, okay, well, I'm ready to make a prediction. I'm ready to run some experiments. And if this is your first time, you can actually get this really fun little guided tour, but we're not going to do that. I think I've used Driverless at least once. I promise. Otherwise, if you've already clicked through it, you can also go to the assistant and they'll give you like these little really fancy bubbles telling you what certain things are. So that's also really cool. So if I click the target column, and that one would be default payment next month. So basically all we're asking is, did this person or did this person not default next month? What that gives you is, it gives you a time column. So if you do, so this is an option if you do want to do time series. Now this is not a time series data set, so I would suggest not using time series on it. Probably not going to give you good numbers. Otherwise, you can use, or rather then next, you can go through the experiment settings and pick how accurate you want it to be, how long you want it to be, or how interpretable you want it to be. Now this is on a scale of 1 to 10, so it's not like I want it to be 6 accuracy, and that's not going to give you like 60% accuracy. It's just how much do I prioritize accuracy over time, over interpretability. So if I set everything to 10, what that would give me is as highly accurate model as I can, in as long as it's necessary to take. But because interpretability is set really high, it needs to be a simple model. It has to be understandable. It has to be interpretable. So theoretically, if you wanted to get super complex, you could go the exact opposite. It would be 10, 10, 1, right? Now I'm going to set this back to something a little bit more reasonable. And we can start with this. So enable GPUs, that's basically just saying make sure to use GPUs. You get a score. This is basically saying which algorithm do we want to use to validate our experiment. So in this case, we're just going to use area under the curve, although you have the option of using F1 score, F2 score, log loss, or Gini, because this is, of course, this is a classification data set. If you were using regression, it could use R2, you could use MAE, you could use, blanking right now, I apologize, but you could use more obvious, you can use, RMSE, RMSLE, to name a few. So basically, different versions of scores to apply to your data set. Excuse me. Once we're ready, we can just hit launch, and what it will do is it will actually start the training of the experiment. Now this can take some time, so I'm actually going to go to a different exposed endpoint, and this one is just because I've run a couple demos on it, so it actually has some pre-baked stuff so that we can take a look. And fortunately, we have, so this is a completed data set, or a completed run through, and you can see kind of the progression here. Now, ultimately, this data set is fairly small. It's about 30,000 rows, so it's really good for demos, but it doesn't have a ton of signal, which is the reason why, as you can see, Driverless AI didn't really find too much going on. So it started with an average, like roughly a 77.77 AUC, or area under the curve, and it ended up around like 80 AUC, and that's mostly because there's a lack of signal in the data set. It also depends on the tuning settings here. So we wanted a lower interpretable model, but we didn't really highly prioritize accuracy either. So if you had set it higher, it would have run for longer and also allowed you to get higher accuracy. And accuracy, by the way, is not just like how many correct over how many wrong, or how many correct over how many total. It's prioritizing the actual value of the score, just to be clear. And so at the end, you can actually see, so variable importance, this is what we were talking about earlier. It's generating those features. And the first one is actually just pay 0. So how much do they pay at the 0th week? But the next one is a value that we created. So numeric 2 categorical weight of evidence. And that's binned across the bill amount number 6 and the pay 0. And basically what it's trying to do is it takes cross-validated sections of the data set and converting the categorical values to numerics. It's trying to find out which ones, which bins are super valuable. And basically it takes those values that are binned together, and that's one category, essentially. So as you can see, it's generating features, and actually of the top, say, 5 features that are important to this model, only one of them came from the original data set, right? So this is just kind of a really good explanation of the fact that we're doing a ton of work for you. And as a data scientist, you can find that one value that's super important, right? You know, if you've been in industry for a long time, you'll probably know that one domain knowledge category where I've known this always gives me at least a 30% boost, right? So you put that in, and it will also be found in your data set, but we can also make combinations of that plus some of your other columns to add even more inference into your data set. So it becomes super valuable, and even more so because you've run it through Driverless AI. So now you have your model, right? You can do a couple different things. You can build the scoring pipeline, which would be output into a Mojo or Pojo, at which point you would serve inference on another machine. You don't need a GPU machine for Mojos and Pojos. So the nice thing is you spend a little bit of money, you use your GPU machine for a couple hours, and then you don't need to use those same resources for serving inference. So you can serve inference on a much smaller machine. So if you are running GCP, you can maybe pay 30 cents an hour, or 30 30 cents a month to serve inference, whereas you spend a lot more, like $14 an hour for a GPU machine, which is roughly accurate. And then afterwards, if you are curious, like maybe you've made your model, you output it, you're like, all right, I'm making some scores, I'm scoring the data, I'm giving my customers some feedback, and maybe for fraud, for example. Or in this case, right, this is very close to, you're basically saying, customer, are you going to default next month, right? So if this was something coming back to a customer, the customer is going to go, why? I don't think I'm going to default. I'm not going to default. And then you get in trouble, right? So that's where MLI comes in. So MLI is the same idea, is machine learning interpretability. Now, this is really cool from my perspective as far as like machine learning goes. Like anyone can build a TensorFlow model. Like, let's just make a mesh of 10 layers and, X number of nodes, and we'll just make it super deep and pass it 1 billion rows, and I'll get some really complex algorithm back that will be pretty accurate probably. The more data you feed a neural net, the better, right? But when someone comes back and says, hey, why did I get denied my loan? What are you going to say? I don't know. The neural net told me. What's a neural net? And other than you, who would know, right? Like some customer off the street's going to go, I think I smell my lawyer coming up. So that's where this comes in, is MLI can actually tell you what's going on. What it builds is it builds several surrogate models of your original model. And for us, that would be mostly XGBoost, so GBMs. But on top of that, right now we do offer a couple other models. So you have the opportunity of using a stacked ensemble of actually XGBoost plus RuleFit, which is basically like a linear model. And then also you can use, we have our self-baked TensorFlow nets that we can actually put. So you can actually use all three if you want. You can use only TensorFlow. You can only use XGBoost. You could use a combination of two. You can use a combination of all three. And ultimately, that can get pretty insane as far as interpretability. It gets very complex. And that's where our MLI comes in, right? So we have a couple different versions of our surrogate models. The first one, easiest one to describe, the decision tree. Basically what this says is at a certain point, what decisions were made and why were they made in a singular decision tree. So we build a decision tree that explains why the model did what it did. So in this instance, at this specific point, at pay 0, it made a decision, which is fairly small, and I apologize, I can't see it, but this one right here, which is basically telling you that at this specific point, for this specific reason, it took a branch to the left, and then now at pay 2, it made the same path down to pay amount 4, and then so forth into your specific, your reason, your answer, whether or not you defaulted, right? We also do this on a much larger scale. So we have a random forest, which gives you feature importance, partial dependency plots, and loco plots. So feature importance is just telling you that at this point, and this is on the original data set. So as you can see, there's none of the features generated by us, although you can also run MLI on the generated features as well. So it's just an option. You can either build one or the other or both. And so pay 1 was the most important, followed by pay 2, and so on and so forth. And these are scaled to 1.0.0, or sorry, 1.00, which is the most important feature would just be 1, and then anything else would be a decimal between 1 and 0. Another cool one is K-Lime. So K-Lime is the same as Lime. Lime is basically a single linear model that is supposed to interpret the model itself, right? What we do is K-Lime, and this was actually built by one of our really, well, a lot smarter than me, engineers, a guy named Patrick Hall. And he basically did Lime, but took it and broke it into smaller chunks. So you have K number of Lime models that approximate the same model. So rather than having a single linear model, you have multiple. And what makes that all the better is that usually a linear model that's going like haywire is super sorry. It's been a long day. So it's super affected by each individual point, right? So at each individual point, it's fluctuating massively, right? So the difference is because of that, if you have it provides a more generalized version of that because you're only having certain subsections that are for each model. So each point is actually generally more reflective of what's actually going on. And what that gives you is the linear reason codes for why this specific point, and this would be ID number 19319. And so the line prediction is saying that it was a 0.01 chance of it being a default, and the model prediction is actual 0.01. So 0.01 of the negative. Sorry, and by the way, actual is 1 is actually meaning they did default. Sorry, this is just way our data set is built. But you can actually see the reason codes as to why. So you can see for this specific point, age had a positive effect on it. All the other data points had a negative effect. And this would be the same effect that you could see in linear betas. So linear regression betas, right? And you can go over like any specific point and make the same, take a look at it and see the same thing, right? So I think I've talked long enough. That's about 45 minutes. So I think I'll open this up to questions if you guys are interested. And yeah, does anyone have questions? I have a microphone, so let's do this here. Oh, you don't need a mic? That's fine.
I can. Curious for your scores. Are these the cross-validated scores, or are they just the direct scores in your training set?
Sorry. So they are cross. So in this data set, I only passed it a train set. So we do use cross-validation to get the AUC. So the AUC is the cross-validated score. Yes.
So when you're picking the scores there, then.
So let's say it's a fold of or five-fold cross-validation. If it's five-fold, then the AUC score that you're getting is based on one of the folds, the holdout fold, the one holdout fold. Yeah. Now, if I were to pass it a validation set, then the score would be based off of that validation set. Does that answer your question? I'm sorry.
Yeah, sort of. It's just like you seem like you're independently tuning the complexity of the model and the how good you want the score to be, but
gotcha.
You could let that, you could just say with cross-validation, you can often skip that step because they're inversely related, right?
Right. So you're talking about this, right? The experiment settings?
Yeah. If I just want the best score, then I shouldn't have to also specify the complexity, I would think. Because
you are correct in a way. So this is sorry. Yes, I follow your point. What I think the difference here is that these settings are telling the machine how to run. So this is more like our runtime settings. I apologize if I wasn't clear on that. Basically, the idea being is that like cross-validation will give you the score for the out of fold data, right? And basically the idea being is if I wanted the difference being is this is how the machine is supposed to handle this. So if I were to say lower interpretability, and it's hard to see up here, but you can actually see like what do these settings mean up over here. I would encourage you to look through this, but basically what it's doing is it's doing certain things. So it's limiting you to certain types of feature generation. It's doing a lot of different things other than just setting the folds, right? So if I increase interpretability, it basically is saying, okay, I can't use certain types of feature generation. I can only limit my ensemble that's generated. So we actually build an ensemble of XGBoost. That's our base setting. Now, of course, you can add TensorFlow into this, or you can add RuleFit. But if I increase the interpretability, then I'm actually saying I can only use, say, a maximum of two models stacked, right? So it's a bit different. It's the tuning parameters here are more for how the machine runs than what's it doing behind the scenes per iteration or per model, right? Is that a little bit better? Yeah. Yes, sir, in the back.
I'm not an expert. I have a very candid question. Coming back on your example of the customer and the credit card company.
Yes.
So the full answer to the customer would be, people like you have defaulted in the past. That's why you're likely to default. That would be the full answer. It's statistical, right?
So if are we assuming a TensorFlow model, or are we assuming, or like, sorry, some just deep learning neural net, or are we assuming through what we did here? Sorry.
What we did here.
Okay.
No, you said, okay, the customer will ask, we want you to explain.
Yeah.
And basically the full answer will be people like you with the same characteristics as you, in the same environment as you are,
mm-hmm.
have had a tendency of X person to default in the past.
Yes.
So you are likely to default. So it's
yes.
based on statistics, basically.
Yes, yes, of course. And most machine learning, algorithms do the same thing, right? Like if you were to use a deep random forest or a random forest, ultimately that's the reasoning behind the random forest. The random forest is saying, okay, well, other people like you have done this, right? The idea behind it also is that with MLI is we're giving specific reasons. So it's not just people like you have done this in the past. It's people like you containing this specific characteristic or this specific characteristics, or you have done exactly this thing at this point in time, and this caused a incremental boost or significant boost in your reasoning for potential default. So MLI basically provides that to you in the sense of saying, we are giving you the statistical reasoning, but also like very granularized, right? So it's this column, right? This specific reason caused this, rather than hand wavy, other people did the same thing, smiley face, sorry, because that's not good. Like ultimately that's going to cause a problem for sure. Yep. Anything else? Looks like no. Great. Yes, sir.
All right. So I thought the MLI bit was pretty cool. So I was just hoping you could maybe explain a little bit more about how that works, because a lot of what I've heard is that it's very difficult to kind of interpret what AI is doing.
Oh, yeah.
So yeah, I don't know. Could you speak a little bit more to that?
Sure. Yeah, I can kind of elaborate a little bit more. So, I mean, the bottom line is what we're trying to do, and this kind of comes back to the gentleman in the back's question, is kind of give a reason as to why for example, someone was declined a loan, or maybe in the instance of like healthcare, right? Why we decided to admit somebody, but also not admit somebody else, right? And in the instance of healthcare, it can be life or death, right? That's the reason why healthcare has been very slow to take up AI, is because there's so many like government reasons that we shouldn't be doing this, and or not that we shouldn't, but that are kind of scary, that are potentially dangerous. And what MLI does is it basically gives you the idea of understanding what a machine is doing, because the machine is bits and bytes at the end of the day, right? I mean, you're telling a computer to go and take some data, which you yourself have made, and find a reason why we want to give this person a room and say, sorry, you're not sick, go home, potentially. And in that kind of instance, it's super important to have things like feature importance. So the idea behind it is feature importance. Now, in this instance, this is from the GBM. So the GBM, you can actually just pull feature importance straight from a stacked ensemble. And it's basically telling you that this specific data point, so pay 0, is very important to the model. Now, the one thing that's tough about this is it's important, but in which way? Is it a positive influence? Is it a negative influence to your specific data point? So we don't actually know whether this is affecting whether or not I predict default in a positive way or a negative way. Negative way meaning more likely to predict to not default, and positive meaning more likely to predict default, right? So this is like kind of the first step, right? So this is what a lot of data scientists have done in the past and do currently, is that they say, okay, well, we have a random forest. We have 1,000 tree random forest. It's super generalized, and it's fairly accurate. It probably, I don't know, I'm making a number up here, but let's say it's 90% accurate. And they ask, okay, but why, right? So we say, okay, well, feature importance. Feature importance is important. So they go and say, okay, well, this specific feature is important. And now we ask why. In what direction is this specific feature is important? So that's where you get some of these surrogate models now become super valuable. Our random forest, we actually do something called loco. And loco actually will tell you the direction in which our features that we generated are important, or rather overall, the whole model, right? So in this case, pay to is super important, but in a positive manner, meaning that if someone paid the second payment, that means they're more likely to not be, rather, so in this case, right, if you paid, you're less likely to default because you're predicting, so more, the effect of pay to is saying that it's, whatever the effect on pay to is that it's more likely to predict default on it, right? Whereas say like pay 0 or your age is having a negative effect. So the lower your age is more likely to say that you're not going to default, apparently, according to this model, right? And we can find reasons to explain that, right? You can say, oh, well, people who are younger probably have less debt, or I don't know, right? Maybe in China that's the case. This is a Chinese data set. I don't know like off the top of my head what the statistics are here, right? But or like say specifically a bill amount, right? A bill amount is this bill amount has a positive effect. So the higher the bill amount, probably the more likely you are to default, right? So that's the loco plots. Partial dependency plots are also super important. Basically what this is giving you is if I take out a data point, how much does it affect the rest of the model, right? And so a lot of these, some of these have actually been used in many instances. Like a lot of data scientists probably have heard or seen of data partial dependency plots and feature importance. One nice thing is that we do it automatically. The other really good one is that we have it visually there. And of course you can use like a Python client to predict it and things like that. And ultimately we also have this, which is K-Lime, which is I think one of the most valuable parts of MLI because it does tell you in a linear method, or rather like in the same way that linear betas would tell you what effect a specific column has had on a specific point. And that would be through K-Lime, which is, I kind of discussed that, so I hope that's kind of a little bit more on specifically machine learning, interpretability, and just interpretability in general.
How are you getting negative p-values?
So these are betas, and so betas can be negative. Yeah. So they're like, if you think about it like a linear regression, right? Like all the betas, you can have negative betas. Yeah, they're not p-values. Yeah. Sorry, was there a question in the back? I know you were kind of sort of. Sorry? You answered it indirectly. Oh, okay. Okay. Yes.
So does it, the way that it generates that is it would come up with samples and then run it through and see how they come out based on how you weight the different features with.
Are you talking about the K-Lime or partial dependency plots?
The thing that's like a linear model that depicts the feature importance.
Yeah.
Is that how that's generated? Like you would basically create some fake data and then run it through it?
So we're actually training on the predictions. So basically like this model is trained on the same data that is predicted. So if you give it a training data set, it will make the predictions on that training data set. And then those predictions are actually the targets for the K-Lime model. So we're not actually training on the original yes/no. So there will be the same wrong answers. So if the model was wrong, also K-Lime will also be training on that wrong answer, right? So it's trying, basically the idea being is that K-Lime is trying to approximate the model as best as it can rather than the data. So if the model's, ideally it wouldn't be this case, but if the model's super bad, then K-Lime will also be super bad in the sense of like not predicting the right answer. But it's still trying to follow the model. So that's the idea behind it. I'm sorry, this lady had a question in the front. Yeah.
So data scientists usually tries many different models and compare and then pick the best, right?
Mm-hmm.
So how, I mean, we are getting techniques developed like every day, right?
Yes.
So how does that protect you from the lawyer when they can say, why didn't you pick the inferior model instead of?
Right. So let me see if I'm getting your question correct here.
So you have a variety. I mean, you're kind of arbitrarily taking a set of models and then try to explain away, but it doesn't really protect you from the.
I think I'm following. And we're not arbitrarily picking the models, right? I mean, this is like ultimately the data scientist has the decision to either use our XGBoost model or use the rule fit models or the TensorFlow models that are built into this specific program. If you were to use H2O3, which is our open source, you have, you know, random forests as well. You have that decision. The ultimate thing is, you know, if a lawyer were to come in and say, hey, you declined my patient, you said no, right? Then the defense is we had legitimate reason, right? And you know, this is tough, especially in the sense of life and death. Now, of course, with say fraud, it's not quite so. Or you know, there's always going to be some sort of danger, and you know, it is America. We sue for everything. I mean, some lady got what is it, a couple $1 million for spilling coffee on her pants. So,
well, for example, some image recognition model, one can detect what is not visible, but it's because it's not visible, you don't really know it's there or not.
Yeah.
So you just have to, you just believe the model by faith. And
I see where you're going with this. Yeah. So I mean, maybe if we take this to the idea of like X-rays, right? You know, a doctor may not see the node, the nodule, or sorry, the cyst, or whatever you may call it, right? Yeah. And in the sense of healthcare, it's very tough, right? Like generally, I would not say go in and take, you know, any machine learning model and go in and say, oh yeah, we're just going to throw this in production. Everyone puts their information in, and we'll just let this decide. Doctors don't have to do anything, right? The idea behind this is going to give you some reasons. So it's going to say, oh, this is going to raise a flag. Say, hey, this person could very well be sick. You know, these are the reasons. You should take a look, right? Or this person is clearly not sick. They don't exhibit any of the symptoms. You know, maybe you do a cursory glance to be sure, but probably not, right? So that's the idea behind it. And with that, you know, our product can give you at least some reason codes behind that saying, these are the reasons why we think they're sick. And, you know, we see this specific little nodule in the image that could potentially be really, really bad. Or, you know, we see this nodule and it means that they're not sick.
But there's no way to disprove.
You're right. And at the same time, you know, that you know, your question really does come up on a question that's, you know, been trying to be answered by data scientists for a long time, right? Is how much can we trust a machine, right? So I agree with you in the sense that, you know, there's always going to be that danger there. But sometimes the best thing we can do is make it as understandable as possible, right? And then potentially, you know, have the fail-safes in place to make sure that there is a secondary decision. So you don't just trust one model, maybe you trust two, maybe trust three, maybe all three have to agree, and all three of them have been trained on different data, so that you're not only, you're trying to generalize as much as possible, right? And so this comes down to, like, this is a very fundamental question to data scientists, is like, how do I make something that can predict, but at the same time, how can I make it so that people accept it? Because if you talk to average Joe Schmo, you know, next door, if I pulled some dude out on the street, that dude on the street's gonna go, what? Random forest, who? Right?
Question of what defines a scientific method, you know? It's the exact same question. There's no universal answer, but it simplifies as much as possible.
You're absolutely right. I agree. Yes, sir. Yes.
So, suppose, forgetting for a second the irony of
de-artifacting the driverless AI,
yeah.
could we cobble together machine learning interpretability module using just H2O?
I believe there's some of the packages are available, and some of them we simply like take and build in. So like we do self-bake a lot of the algorithms ourselves. So some of this stuff is our own IP. I'm sure that a lot of people have done interpretability. Don't get me wrong. Like Lime itself, not K-Lime because that's ours, but like Lime itself is open source. So there's plenty of people who have done all kinds of things. Yeah, and I'm sure if you searched, you'd be able to find it. Yes, sir.
Can I get that for the audience?
Yeah. Yes, sir, in the back. Sorry, I did ignore you originally.
Here you go. What kind of performance overhead do you see from inspecting the data as you're training on, like to get these to like inspect the black box? Like what kinds of extra performance overhead do you see while training or while going through the process?
Are you talking cost? Are we talking time? Are we talking?
I guess whichever is the most relevant or the most like.
Cost-wise and time-wise, it's kind of correlated because obviously the more time you spend on the box, the more cost there is, right? MLI is also is being optimized for GPUs, but at the moment it's run in CPUs. But because of the type of algorithms that we're using, because they're mostly linear and or widely parallelizable, the amount of time that it takes for the algorithm itself to run is fairly short. I think the last time I checked, running a 15 gigabyte data set, which is not tiny but not also enormous. It was running maybe 30 minutes to an hour. So I mean, ultimately, the runtime for the actual experiment was roughly about 6 hours if you ask for a fairly complex model. So the interpretability part is actually pretty lightweight as far as time goes and overhead. Mm-hmm. Yes, sir, up front.
Let me get you the mic.
Can you explain again what was the difference between the Lime and the K-Lime model?
Yes, Lime is a single linear model that is supposed to approximate the final model that you get. So if it was a random forest, or in our case, a stacked ensemble of XGBoost, could you just push the bottom of the mic? There's a button. Right at the bottom. Perfect. Sorry, there's like some feedback. But yeah, so Lime is a single linear model. K-Lime is going to be K-full, or K-linear model. So the number of linear models that you can actually choose this. So you can, one of the settings you can pick is how many linear models to use in the ultimate K-Lime surrogate model. So it would be like, you could potentially have like 10 linear models that approximate the same XG boosted model, or like stacked ensemble, or you could do like 3. And I believe our default is 3, if I remember off the top of my head. But you can pick that. So it's just X number of models, or X number of linear models to approximate the final ensemble.
So it's like the bootstrap for random forest, but with linear models, and you choose different features at the end. Because if not, the values of the betas would be the same.
Sorry, say again? Sorry.
So between each model, you change the features and also the data. You do it randomly, or?
Yes, it's randomly sampled.
So like random forest, but with linear regression.
Yes, essentially yes. Yeah. Yeah. Yes.
How does it? Let us say we have mixed data, like you showed in the earlier.
Mm-hmm.
So it has numbers, characters, and all that stuff. How does it read different data types in the same field?
In the same field. So in the same category or in the same row?
Let us say address, right? Address has numbers, street names, and state, and all that stuff.
I see. Okay.
Yeah. So how do you categorize those?
Generally, so in the instance of like an address, it's likely that it would be converted to a string. Yeah. I mean, in most schematic formats, like in just like plain SQL, that's probably what'll end up happening. You like SQL like in a SQL schema, right? You're not going to get like part numbers, part thing, part the other thing.
No, the question where I'm coming from is you said you can actually read data from big data or whatever servers you already have.
Yes.
So most of it is JSON format, right?
Yes.
So it can be multiple fields in the same file. So how do you train the system to read different JSON formats? Because JSON doesn't have a particular format, right? So it can be any different fields, any different files. So how do you handle that?
So at the moment, I don't think we actually, so the data sets that we can import, or the data storage types that we can import from are mostly blob store, so like HDFS or S3 or GCS, which would have a file, right, which theoretically is schema formatted, so like CSV, TSV, Parquet, what have you, right? Otherwise, there's SQL ingest options inclusive BigQuery or Snowflake, and these are data warehouses. So when you import from those file systems, on the back end, what we do is we actually can we make sure to add the schema so that when we bin it in PyData table, there is that schema, and so that we can understand which ones are which. Yeah.
So even with the JSON, you can do the same thing. You can create your schema, then you can actually load.
Yes.
Okay. Yeah.
So data cleaning is still in the side of the companies.
Correct. Which is actually one of the reasons why. So part of the reason why I recommend this is because you can actually do, like a lot of people have their data munging and data cleaning in Spark as it is. Like a lot of pipelines use Spark. So generally speaking, I would say that's one good method of cleaning your data and putting it into Driverless AI specifically. Now, if you were running the open source, then the recommendation would just be leave it in Spark. You can ingest your data in Spark, clean your data in Spark, create your algorithms in Spark, and then output the models. And it's like H2O is fully optimized to run in a Spark infrastructure. So it kind of depends on what your business needs are. Driverless AI is a singular thing that does a lot of the data science for you. So if like you really wanted a full pipeline, that's what Driverless AI does. Whereas H2O is much more like a library, right? H2O3 is a library. It's allowing you to kind of self-build your pipeline around it, right? So a full pipeline could look something like ingest data into H2O sparkling water, or just in Spark in general, munge it, clean it, put it into Driverless AI, or stay in Spark and run H2O and the algorithms in H2O, and you'd have to build that pipeline yourself. Yeah.
Is it more disclosure to the public who is using the AI, the Driverless AI, so they can have access to the components of the model?
So it is our IP. So it is mostly private. That's like, I mean, this is what we kind of make money off of. So yeah, if we did give it out, then there'd be kind of no point of us selling it. So yeah, but I mean, if you are interested, if your company is interested, there are plenty of options. We have pay-as-you-go options, so you can just simply log on to your cloud provider of your choice and go in and play around with it for a couple hours, spend maybe $30, and you've gotten kind of an understanding of what Driverless AI is. Plus, you could even use the Python client behind it, which is free to download. Basically, like I apologize, I had too many tabs open. You can just click PyClient and it'll download the Python client to your computer. You can install it. It's a wheel, so pip install said wheel, and you can have it there.
And to add to that, you can request yourself a trial license valid for 21 days. If you go to h2o.ai/DAI, you can download Driverless AI and run it as a full production model or a full production software for 21 days without any charges.
Yes, that too.
Could you use a model to pick how many days the trial should be? How many? You use a model to pick how many days the trial should be?
The model will last for 21 days as well. So if you were to output a model and try and infer or do scoring for more than 21 days, then the model stopped working. Yes.
The H2O can support our own custom algorithms, or is it? I mean, you already might have some built-in algorithms.
So driverless, correct?
Yeah. Do we need to use whatever is existing already, the algorithms, or can we create our own custom algorithms?
So we do self-bake the algorithms ourselves. So yeah, if you were to say create an experiment, then yes, you would be using ours. And we don't allow for input of other other like user-generated algorithms. No.
So we can't customize anything.
Yeah. So you wouldn't be able to put like say a scikit-learn model in there. Yeah, it would be ours, our models. Yeah.
So yeah, what if I want to like say log transform something, but I want to use the scoring function like that's appropriate to the original data, so I can't do that basically.
Sorry, I heard like half of that.
Oh, sorry. So suppose I do some transformations originally, like I do some log transformation of something to make it Gaussian or whatever before I feed it in. But then I want the scoring function for the original untransformed data because maybe I prefer that. So I can't, okay, put it this way. Could I at least customize a scoring function? Because that would be more useful, I think.
I would struggle to find the reason why, mostly because like if you're running it through Driverless AI, right, the end model is trained on all the auto-generated features. So they're like if you were to create your own features and you want to train a algorithm without using.
No, I like your features. I just want to have my own scoring function. Is that possible?
So your own scoring function, meaning only scored on the original features.
Well, I just want to make something up because maybe I want to have a totally new scoring function. Okay, maybe for the next version.
Yeah, I don't think we have that at the moment. I would love to maybe chat offline about this potentially. It sounds interesting. I would need to have maybe a bit more explanation on it. Yeah. Okay.
We have time for one last question.
Yes.
Was that a question?
No. Is Mojo the only way to export?
Python as well. Yeah, and I believe we also have a Java scoring package as well. That was an easy question. I like that one.
So no pickle.
No.
Export a model.
I believe part of the jar file is also a pickled version. No. We just jar it. Yeah, so it's just Java. Or in the Python version, it's a Python scoring pipeline, which I believe actually might use pickle. Off the top of my head, I just don't know. So actually, I apologize. I don't know off the top of my head. Okay, so maybe a little bit more difficult of a question. Awesome. So yeah, I hope you guys enjoyed it. It sounds like you had a lot of questions. So yeah, hope you guys have a good rest of your night. If you guys are going to be at Google Next, come say hi. Otherwise, you don't need to attend the session because you've basically gotten everything. So yeah, thanks.